Hey guys, we're going to do the a couple problems from the homework on the rotational dynamics packet. That was a green one you guys got. So let's we're going to work. I'm going to work through 3 problems, getting progressively more challenging as we go. I think I'm going to start with number 4, do number 6, and then we'll do number 8. So 4, 6, and 8. I'm going to leave the rest up to you guys. Remember, if you are trying to do the homework, can't figure it out, don't know what to do. Where do you go? Who do you call? Me. Tutoring. Okay, let's start. Number 4. Diagram shows we got 2 massive masses attached by a light string that passes over a massive pulley. I'm not sure what's massive about it, but whatever. But it says it's massive. The radius of the pulley is 0.8 meters. Not that massive, but whatever. And it has a rotational inertia of 25 kilograms meter squared. So our I of the pulley is 25. It has a radius R of 0.8. This pen. All right, and then let's see. The tensions shown in the diagram are T1 -5 and T2 is 12. What is the acceleration of the blocks? Okay, well they're all tied together, right? So if we find the acceleration of any one thing, then we're going to find the acceleration of everything, right? So what we're going to do in this problem is try to find the acceleration of this pulley. I will note this is really weird that I just wasn't thinking when I wrote those numbers in. -5 for T1 and +12 for T2. That's kind of like impossible. It should have just been like -12 and +12, but I guess I just brain farted when I wrote the numbers in. Because you can't have like different tensions in the same rope. Well, you can in real world situations, but not in like our level of physics. We typically have the same tension everywhere within one string, one rope. But we'll just pretend it's not a big deal. It's just I just didn't think about it when I made the problem, but whatever. All right, so we are going to use first thing we're going to do is find the total torque, right? So these ropes are torquing the pulley, right? This rope here is kind of torquing the pulley in a certain direction. T1 is -5, so it's torquing it in the clockwise direction, which is this way. T1 and then tension 2, right, is pulling up this way. It's going torque 2 is going this way. So this is torque 1, right? Torque 1 is pulling down this direction. And torque 1, and then which rotates it this way, which is clockwise and negative. Torque 2, or tension 2, is up this way, which is going to make the wheel spin in a counterclockwise direction. Right? So you see how tension 1 is going from left to right up here, and if you kind of trace its path, it's going to go over the pulley this way, right, over this direction here, which will make it go clockwise. And if you look at tension 2, is going up, right, up the rope here. If you follow its path, it's going to go around the pulley this way, which is a counterclockwise direction. That's why it's positive. All right. So those are the forces that are going to cause the pulley to rotate. And a force that causes the pulley to rotate is called the torque. So what's the net torque on the pulley? Well, we have Fr. Now sine theta. All right. Well, so sine theta in this case is going to be 90 degrees. It will be the angle because it's all tangent to the circle. At any one point, draw pulley again. Here's the rope going over the pulley. At any one point, we typically think of kind of like right here maybe. At that one point, the tangent to the circle, the rope is tangent to the circle at that point. It's going like down this way, right? At an angle. Whoa, what is here? At that angle like that, which is tangent to the circle. So if you think about here's the radius, then right, that radial line from the pivot point, the center of the circle, and that radial line to the spot where apply the force, that angle there is 90 degrees. It's a terrible drawing, but I hope you get the idea. So if we have a rope going over a pulley, everywhere on the pulley that it's applying force is tangent to the pivot point. So it's always going to be 90 degrees in this situation with a rope over a pulley or a string, whatever. All right, so it's sine. So I'm not even going to write in sine theta. I'm going to leave it like Fr. And it's force 1, and then we're going to have plus Fr, and that's a force 2. Now, force 1 is tension 1, right? That's F is tension force, is the force 1, and tension 2 is force 2. So we're going to have our net torque then is our total torque. You just add all the torques up, right? This tension force is causing a torque, and this tension force is causing a torque. So they are our total torque. We're going to add up the total torques. So F1 is -5 times 0.8, and then we're going to have plus 12 times 0.8. And we do the math here. Our total torque is going to be 5.6 Newton meters. And where'd my calculator go? I'll use my phone for now. Oh, it's in here, I think. I'll find it. I'm going to pause real quick. Alright, I got my calculator ready to go. So now we have our total torque. Now we're going to use Newton's second law of motion, but the rotational version of it. So it's alpha equals the net torque over moment of inertia I, which we already know, right? The problem told us what that was, 25 for the pulley. So again, if we can find the acceleration of the pulley, then everything's attached to the pulley, right? The strings are passing over the pulley, and we assume there's no slippage, right? Imagine if the pulley were this hand. This is terrible. I have a better. If the pulley was this bundle of markers, and my finger was the string, okay, then if the pulley is kind of rotating together, right, that's one thing. But what if the string kind of slipped and didn't turn the pulley? That's called slippage, right, or slipping. Well, we have to assume that that's not happening, because if that did happen, it would everything would go out the window. We'd have to, couldn't really solve it then. So we have to assume, and a lot of times problems will say, a string or rope passes over a pulley that doesn't slip or something like that. So we assume that there's no slipping. So as the pulley turns, so do the ropes then move, and which also moves the masses because they're all attached to each other, right? Okay, so they're all attached. So the net torque we said was 5.6. The moment of inertia of the pulley is 25. And that's going to give us our angular acceleration, and that is 0.224. And that's in radians per second squared. But it asks us to find the acceleration of the blocks, and the blocks aren't spinning, right? They're moving in a linear or translational fashion. So radians per second squared for these guys doesn't really make a lot of sense. So we're going to convert that into linear acceleration, which is a alpha r. Again, we're going to use the radius of the pulley, which is 0.8, because we want to convert the acceleration of the pulley to a linear fashion, which again will help us will tell us what the linear acceleration of the blocks are. 0.8 times alpha was 0.224. Squeeze it in there, and that's a times, not a negative sign. 0.8. Oh God. Okay, so this is 0.224 times 0.8. That's, I know my handwriting is just beyond awful. Sorry. Okay. So we get 0.8 times 0.224, and it's about 0.18. 0.18 meters per second squared. That's the acceleration of the blocks. In fact, the whole thing, whether it's the pulley, the string, or either block, it's all accelerating at in a translational speed of a translational acceleration, or linear acceleration, all means the same thing, of 0.18 meters per second squared. All right, so what do? We started off with finding the total torque that gave us the forces. Tension is a force, so we use those total forces to get our total torque. And then we use Newton's second law to find the angular acceleration, because we knew the moment of inertia. So, and then once we had the angular acceleration, we use our conversion to convert from angular acceleration into linear acceleration. So 3 steps. Hopefully you're able to follow along with that. All right, so now I'm going to do the next problem. I'm going to do number 6. So I'm going to pause real quick, and then I'm going to pick back up. I'll be at number 6. All right. All right, here we go. Number 6. This one's kind of a doozy. All right. So hang with me here. There's several steps to this problem. Probably, I kind of broke it down into 3 steps. All right. So it's asking us, we got the cylinder or whatever. It tells us the mass of the cylinder, 4 kilograms. We get the moment of inertia. It doesn't tell us what it is, but it tells us it's mr squared over 2, right? So it's like one of those common shapes, and it's 1/2 mr squared, or mr squared over 2, same diff. It's got a light thread wrapped around it. Okay, so tied around it. And then we got this mass that's hanging here. A mass of 2 kilograms hangs, And it wants to know the acceleration of the mass. So what's A of the mass when it falls? Okay, and then also what's the tension in the string? Okay, we want to know all these things. Okay, now again, so long as we find the acceleration of anything, right? If we can find the acceleration of this pulley, its angular acceleration, then we know the acceleration of the mass because it's all connected, right? So we just got to find the acceleration of one of these things, and we'll be good. And then once we find the acceleration, finding the tension is pretty easy. First thing we got to do here is review on how these pulleys work, right? We want to think of them as a system, okay? We want to think of it as what's literally everything, you know, part of. So let's define the system first. In this case, I'm going to define the system as this mass and then the rope, all right? And then that's pretty much it. So what is the net force? So step one. All right, step one, find the Newton's second law equation for the falling block, okay? The system of the block and the rope, okay? Hey, all right, so we have the net force equals mass and acceleration. That's an equation that we should have burned into our brains. And then we think, okay, well, what are all the forces on the block? I only want to think about the block right now, okay? Nothing else. Well, there are two forces on the block. We have its weight pulling it down in, well, that's a terrible arrow. Weight pulling, I gotta re-click my pen, that is annoying. Weight going straight down, that's better. mg, and this tension force going up, which you don't know what it is, right? So, alright, we have our tension, let's call up positive. So the forces are, there's two of them. The force of tension up minus mg down, and because it's down, right? So minus. And then that's it. And then that's going to equal negative ma. Why negative? Well, what direction is it accelerating? Down, right? So we're calling everything down is negative. Everything up is positive. So we have one positive thing, the t, and we have two negative things, the mg, because that's down also. Right? G is down, the acceleration of gravity. And then this one's also down because its acceleration will be down. Okay, so we got it. This is very important to get the signs right. If you miss this startup right here, you'll never get the right answer. So you got to be clear on the direction. Super, super important. Okay, we're going to rearrange this for t. So I'm just going to plus the mg over to this side. So I'm going to get t, it's a tension force, right, equals mg, which is on this side is positive now, right, minus ma. Because it was negative on this side, we added it to this side. So now it's positive mg minus ma. This is step one. We've got to find our tension force. Now we're going to remember that torque is force times radius. Sine of theta. But again, as we discussed in problem number 4, look at the angle here, right? Here's a pivot point, draw the radial line. This angle is 90, so it's sine 90 is just 1, so I'm not going to worry about it, okay? Technically, it's in there, but it's just going to be 1, so who cares? All right, so what is the force? Well, we just found the force, right? The tension force, the torque on the pulley. Let's go back a little bit. I'm going kind of fast. Getting excited. What is making the pulley spin? It's a torque. That's what torques do, right? They make things spin. What's causing the torque? Well, it's a tension force, right? The tension is the string. That's what's wrapped around the pulley. Is this string, which applies a force of tension, which then causes a torque on the pulley, makes it spin, makes it rotate, right? Okay, well, what is that force of tension? Well, it's right here, right? It's mg minus ma. So I'm going to replace the torque of that, the torque on the pulley is the tension force. That's what's causing it, right? The tension force. So the force is this, mg minus ma. I'm going to replace the F here with mg minus ma. All that times r. Okay? All that times r. All right, that's step 2. Realizing here that we can replace this equation here with the tension, and that understanding that is the force that's causing the torque. So I'm going to substitute in for this F over here. I'm going to plug in the mg minus ma into the F. And then multiply that by r, that'll be my torque. Alright? That's step 1. Well, steps 1 and 2, I guess. That's step 2. Alright, step 3. Newton's second law. You knew it was coming. Angular acceleration alpha equals the torque, the net torque, over the moment of inertia I, which the problem told us was mr squared over 2. So I'm not even going to write I, I'm going to write mr squared over 2 because that's what it says it is. Mr squared. And I'm going to do it this way. I'm going to do 1/2. Same thing, right? 1/2 mr squared over 2 is the same thing. Okay. now I'm going to substitute in some stuff. I'm going to plug in this equation here for my torque, because that's what it is, right? There's only one thing causing a torque in this problem, and that is this rope, this string. So the net torque is just the one. There's only one torque, right? So my alpha then is going to be mg r minus m-a-r. So what I did with the r's was I distributed the r, right, to both of these terms here. I distributed them, right? And all this is going to be divided by 1/2 mr squared. Now we got an r in both terms up above on the numerator and an mr squared down below, so these r's will cancel. And it's going to get rid of one of these r's, so the squared part is gone, but the rest of it's still there. All right. Now I'm going to do something that's a little weird here. I'm going to go ahead and replace the alpha. Remember, we're not looking for alpha, we're looking for a. We want to know the linear acceleration. In terms of the acceleration, not angular acceleration, just a. So recall that a equals alpha r. And if you rearrange for alpha, we get a over r equals alpha. So if alpha is a over r, I'm going to replace this alpha here with an a over r. Now what's going to happen in this r? This is now uppercase r, lowercase r. In this case, it's the same r. All right, so equals mg minus ma over 1/2 mr. Now these r's are going to cancel, right? Because I have multiplied both sides by r. Now these r's cancel. And this r cancels. So now they're all gone. So now I got rid of my r's. So it turns out the radius doesn't matter. Weird. Okay. All right. And then I'm left with, I'm going to write one more line down here. Now I have a. So now I don't have to do a conversion later. I've already kind of incorporated the conversion from angular to linear into the problem, and it just kind of helps out with the math here. It gets rid of the r's for me. All right. Now what's next? Okay. Now I have to rewrite it here. I have a equals mg minus ma over 1/2 m. Well, guess what? I know all these things. I know the mass of my object here. It was little m, right? That was the mass. Remember, this came from the force of tension, which was on this mass. So these little m's are 2's. This big M came from the moment of inertia of the pulley, which is the big M, which is 4. So I know all these things. I know little m's 2, right? G is 10, and then big M is 4. And there's A and A. Well, those are both the same term, so I can solve for A. So let's plug in some numbers here. So I'm gonna take this. I'm gonna go up, way up here, just so I can kind of have a nice, flowing down here. So A equals little m was 2 times G is 10. Minus m was 2 times a, I don't know what that a is yet, divided by half of big M. Well, big M was 4, half that's 2, right? So I have 2 here. All right, so let's simplify things down. A equals 2 times 10 is 20, minus 2a over 2. I'm going to multiply both sides by 2 to cancel the denominator. Multiply by 2 both sides. These 2's will cancel. I get 2a equals 20 minus 2a. I'm going to add 2a to both sides to cancel this side's a's. Right now I get all the a's on one side. I want the a's all together, right? 2a plus 2a is 4a equals 20. Divide by 4. Divide by 4. These 4's cancel. A is 5 meters per second squared, and I'm already in the right units. Don't have to convert to anything because I kind of already did it earlier. So there we go. Lots of steps. Understandably confusing, okay? But if you can see a pulley and understand, okay, you should probably recognize right off the bat that if we're trying to find acceleration, we're going to need Newton's second law at some point, right? We need this guy over here. You might think, okay, wow, well, I don't know what I is. Just gives me this equation, so okay, I'm going to plug that in. I got to find the torque. I got to find the torque somehow. Okay, so then you got to recognize, okay, I got to find torque. What's causing the torque? It's the string. The string is rubbing over the pulley and making the pulley spin, right? Okay, so the string, what kind of force does a string or a rope apply? Well, that's a tension force, right? Okay, how do I find the tension force? And then you got to think back to what we did last semester with the tensions and stuff and the pulley systems. and think, okay, what's my equation for my Newton's second law equation for the total, forces and accelerations on that object on the pulley, and that's where we come to here. And so we work our way through, we get the tension, and then we follow the steps. Now we're not quite done. It also wants to know what the tension in the string is. So now this is easy. I'm going to go back to this equation right here. Excuse me. And now I know what A is, so I can just solve for T. So T equals mg minus ma. So T is little m was 2, G is 10 minus 2, and now we know A is 5. So this is going to be easy. So this is going to be 20 minus 10. So the tension force is 10 newtons. So there we go. This answer here and an answer there, and we got it. All right. So long one, yes. But what I want you to do is just work your way through it with me in the video, okay? And then what you can do is you can make another problem just exactly identical to this one, and just put different numbers in there, right? And then that's like a little extra practice, okay? And then see if you can work your way through it without, watch the video the first time, and then make a third one. Do it a third time with all new numbers, and then don't watch the video anymore, okay? Try to do it on your own. If you can do that, then you're probably good, okay? 3 times around. Do it a 4th and 5th time if you want to, if you're really hardcore, all right? But you're not going to learn this stuff by just doing it one time watching the video. It's not going to sink in. It's just not. Repetition is key. I'll shut up now. All right, one more problem, number 8. All right, come back for number 8 when you're ready. All right, guys, we're going to do the last one, number 8. Last one of this video anyway. So it's basically the same apparatus as we have in our laboratory, our lab this week. We have this, T-shaped apparatus with this thin rod on the top of 2 spheres attached to either end. So we have hanging masses, same diff, right? All right, so, and, string out around it, around a pulley, hangs off the edge, falls, blah, blah, blah. Okay, we know the drill. Now, it says the center of the rod is fixed to a light vertical pole, a radius 0.1 meters. So this pole here has a radius of, okay. What did I just do? I don't know what I did. All right, there we go. I pressed the button. That vertical pole has a radius of 0.1 meters. Okay, all right, so, our end goal, part A is easy. It says, what is the moment of inertia of the assembly of the 2 spheres? All right, so when it says assembly of the 2 spheres, it's talking about this top part here, just this part up here. And we don't know the mass of this rod, and it says it's a light rod. When you get physics problems on the AP test or my test, and they say it's a light rod, what they mean is, don't worry about this, ignore its mass. Don't worry about it. It might as well have 0 mass, right? Just like when you get problems that say things like smooth. It's a smooth surface. When they say smooth, they mean there's no friction, right? So it's like they're code words. Why can't they just say it? Can treat it as a massless thing? I don't know. They're jerks. That's what they do. But it says light rod. Basically mean okay, well it's got no mass then. So our total moment of inertia, net sigma I, right, or the net I, is each individual moments of inertia added up. So this sphere here has got a moment of inertia, and it's mr squared, right? Because we're treating it as a single point, right? It's treating it like it's got all its mass is right in the middle. Remember, it's not spinning. That sphere isn't spinning. It's rotating around on this T-shaped thing, right? So we're going to treat it like it's a single point, and we're going to add it to the other sphere. It's mr squared. We're just going to add these things up. So the total I, net I, of this assembly of spheres here at the top is going to be, each of them has a mass of 3. No, 3. Now it says it's r squared. So, okay, its distance from its axis of rotation. Now its axis is here, right? Excuse me, in the middle. And this total rod has a length of 2L, where L is 2. So that means that this is 2 squared plus 3 times 2 squared, right? Since the radius is 2 meters to the center there. So 2 squared is 4 times 3 is 12. 12 plus 12 is 24. So our total I is 24 kilogram meters squared. All right, so kind of a weird thing. Again, I know a lot of y'all think, oh, do I got to use those weird equations we had where it's like 2/5 mr squared and 2/3? only if that's the object that's spinning. This object is basically in orbit, right? It's making revolutions around the center. It's this sphere, I keep pointing at the screen, you can see me, that sphere is not spinning, right? It's rotating around something else. So we don't need to worry about the 2/5 stuff. It's just a single, treat it like a single point. All right, so that's our total I. All right, now we're going to go to part B. Part B is very similar to the last problem we had on number 6. Similar, not the same, but similar. What is the acceleration of the large mass as it falls? Okay, well, we are going to treat this mass in this rope as kind of the system. So we got to find out what is a Newton's second law, net forces times mass times acceleration, just for the block, only the block. Well, it has tension force up minus its weight down, just like last time, equals negative ma, right? That is the same equation we had last time. We're going to add the mg over to the side and get our tension force, T. Now that tension force is the force that's causing this vertical pipe here, or whatever, to rotate, right? That is the force that's making that happen, okay? So, when we think about Newton's second law, for rotational motion, we have alpha equals net torque over I, which we know what I is now, though, right? It's 24. So it helps us a little bit, makes our life a little easier for this problem. I is 24. This is again, it's a light vertical rod, so we don't know what its mass is. It says it's a light vertical rod, so basically what it's saying is it's massless. Don't worry about its mass, right? Now in our lab experiment, it's obviously not massless. It has some mass, but we're gonna, we're gonna approximate, okay? Which is what we're doing here, which is fine. All right. So what is the torque? Well, this is the torque, right? It's mg minus ma times r, right? Remember torque. Torque is force times r. This tension is the force. So we're going to plug this in for the F, right? Since that is the force, times r to get our torque. So I'm going to replace this T here, this funky T here. So the alpha equals mg r minus ma r. Just like last time, all over 24. Okay. And where did the r come from? I remember I just distributed the r's, right? So if I'll go ahead and write mg minus ma, all that times r. I just kind of distributed the r's, which I didn't really have to in this problem, but whatever, I just did it anyway. Times r there, times r there. All right. The r is 0.1. Now it's different this time for the vertical pole that we're spinning. Okay. So now when it comes to this, or actually, yeah. Okay. So for the tension force here, applying its force to this pole here. So the r now is 0.1. It's not 2 anymore, right? It's 2 over here for the moments of inertia on those spheres that we're rotating around. But now we're talking about torque on the vertical pole. So now our r is going to be 0.1. That was the radius of the vertical pole. Okay, and now we can start plugging in some numbers. This is I should have wrote big M here, because this is the mass of this block, right, which is 4 kilograms. So now I'm going to plug in my numbers. I get alpha equals, let's see, big M is 4 times 10 times 0.1 minus 4 times A, which I don't know what A is, right, times 0.1 all over 24. And I'm going to go ahead and replace that alpha with the same thing we did last time, A over R. So if you didn't watch problem 6, you skipped problem 6, which you shouldn't have. This becomes A over R because we know A equals alpha R. If you rearrange for alpha, then A over R equals alpha. So I replace alpha A over R. That way I can get all my A's together. And again, the R, I'm going to go and replace that R with 0.1 also. It's the same. Might as well keep all my R's at 0.1 here, since that's the radius of the vertical pole. Okay, there we go. Now let's simplify this stuff down. This is A over 0.1 equals, okay, 4 times 10 is 40, times 0.1 is 4 again. This is 4 minus 0.4A over 24. I'm going to simplify my sides again, kind of like last time again, right? Times 24 both sides. Times 24 this side. 24s will cancel here. I'm running out of room. I'm going to come up in this little corner. I don't want to erase anything. I'm going to come up here right above my picture. 24 times A divided by 0.1. That should be 240. 240, right? So let's see. 24 divided by 0.1. I don't know why I'm punching this in. I know it's 240. 240 A equals, what's left on the right hand side? 4 minus 0.4 A. Alright, well, I'm going to add plus 0.4 A both sides. I want to get all my A's together here, right? That's 0.4 there. Alright, so these cancel. 0.4 A's both sides, so it's 240.4 A's now, right? If I have 240 apples and I add 0.4 of an apple, I get 240.4 A apples, right? Equals 4. Now I'm going to divide by 240.4 both sides, and I'm going to get A equals a very small number. 4 divided by 240.4, and I'm getting 0.166. 0.166 meters per second squared. Very slow, almost as slow as what we were doing in class, right? Now, ours was even slower because in our class, the mass we were hanging down from the pulley was only half a kilogram, not 4 kilograms. Although we did hang less mass up here, so it had less inertia, but also less tension. So ours is even slower. Plus, we had the mass. You know, we weren't considering it a massless rod, right? It has mass in reality. So we're getting even smaller numbers, but it's kind of similar to this problem. Now we're not quite done. It also wants to know. Oh no, it's not asking for tension, is it? I thought it was going to ask for tension. It does not ask for tension. What is the acceleration of the large mass as it falls? Oh, there you go. Okay, there's our answer there. 0.166. And that was the inertia here. Let's go ahead and find tension because it's fun. Tension was mg minus ma. Now we know what A is. It's 0.166. And so we plug in there. Tension is, this mass is 4 times, that's g, not g, times 10 minus 4 times 0.166. So tension will be whatever that is. That times 4. Ooh. It's 4 2. I'm plugging stuff in the calculator. Oh, it's 0.01. I'm sorry. I didn't see a 0 in there. So it's very close to what we were getting. Is it 0.0? Why does it do that in racing? 0.0166. Sorry about that. So I caught it. We're all good. Alright, so that number times 4, and then 40 minus that. So it's almost as, gosh, the tension is almost as much as the weight is, right? Tension is 39.93 newtons. So no wonder it's barely going, it's accelerating so slow. The tension force is almost the same as the mass itself, or as the weight itself, which would make sense why it's going so slow. Alright, so there we go. A lot of steps, very similar to the last problem, but hopefully you were able to kind of follow those things along. And you know, work through it. If you're not sure of any steps, please come see me. And hope that helped. A long video, but sorry, these problems get a little in-depth, a little you know, complex. So, all right, have a great day, guys, and I'll see you guys next day in class. All right, bye-bye.